Is Yamin Zhu here from Shanghai Jiao Tong University?
怎么跑？
对啊，我也准备走了。
我靠，这边都没人干了。
你和那个？
我在前面弄的。
对啊，那个。
谁在这周边来？
对，他。招生。
Hello. Okay. Hello everyone. My name is Liang from Xiamen University. Welcome to the session of network deployment and quality optimization. Well, the first session this afternoon, and the first speaker is Alan. He is a PhD student from Central South University in China and Hong Kong Polytechnic University. The title of his talk is Deploying Wireless Sensor Networks with Fault Tolerance for Structural Health Monitoring.
Good afternoon, everyone. I am going to present my paper on deploying wireless sensor network with fault tolerance for structural health monitoring. This work is done between Hong Kong Polytechnic University, Professor Jian Nongca, and Guojing Wang, Central South University, Changsha, China. So, the outline of my talk, I will first discuss shortly what is structural health monitoring. Then I will focus difference between SHM and WSN application. And then I will show my main works on WSN deployment for civil infrastructure. Then I will show some work and simulation and implementation. And I will conclude the paper and show some future works. So first of all, we need to know what is SHM. It's a type of system that provides information about any damage occurring in a structure. That can be buildings, bridge, aircraft, nuclear plants, and any kind of structure, civil infrastructure, structural engineering infrastructure, also mechanical engineering, some other infrastructure also can be included here. So the interest is we need to know in advance some information that is damaged, that is a significant changes in the structure. Some changes we can provide some information in advance before it is occurring really. So why we need SHM system? We can see that here one bridge is collapsed in Minnesota in USA in 2007. Another bridge is collapsed in Penghuang in China. This is another bridge also is collapsed in Zhuzhou in China. So there are many kind of aircraft events. Is every year, even every month, are collapsing over the world. So here, so we analyze. We have the information that about 25% aircraft is destroying over the world is because of structural failure. So there is a need of structure health monitoring. So currently, traditional civil engineering, structural engineering method have been using. Now we are going to find how we can use WSN for those monitoring. Here, how to design a SHM system. So in SHM system, we have structural phenomena to be monitored. We need sensor, time strategies, and damage detection algorithm, and we need to find the protocol for data transfer and storage mechanism. There are many data transfer and storage mechanism. This kind of concern is already established in WSN. So when we focus on sensor, there is sensor, CPU, and wireless transceiver. So the concern is how to deploy the sensor on the structure, on different kind of civil infrastructure. So if we focus SHM with WSN other applications, we can see that in other applications, usually our concern is energy imitation. We usually focus on event tracking, tower tracking, but here we focus on vibration characteristics. Also can be image, acoustic. So our concern is damage occurrence, not event detection. So this damage occurrence need a lot of data, a sequence of data to be computed in centralized. So there are more challenges. And now how and from where we can get that data from the civil infrastructure. So now here we can see there's one bridge. Here the vibration can be one type, and the same vibration we cannot get here. Maybe it can be influenced by the civil infrastructure. So if we usually we use the traditional deployment method, we cannot guarantee that the vibration data can be the same for all the sensors. So there are the challenges. Now the challenge is how to sensor placed in civil infrastructure. The placement is other WSN applications. We can find random, uniform, rectangular, circular, these kind of things. Can you imagine that this traditional method can be used for SHM, which can be anywhere, anytime? We can place the sensor anywhere in the structure, anytime. So if we want to say that anytime, anywhere can be placed sensor in a infrastructure, we cannot guarantee that. These difficulties can be appeared there. The monitoring at some specific locations where the damage sensitivity is high. Usually if we focus on this deployment, maybe we cannot get this damage sensitivity. Since I already said that the damage sensitivity can be different in different location in the different infrastructure. So we have to concern about this. Now, we need to focus and we need to follow the engineering-driven deployment. Since there is civil engineer, structural engineer, we need to follow their method. We cannot provide different method for WSN. We need to come out with their approach. So the engineering deployment, they followed sensor are placed at optimal location in order to achieve the best estimate of physical properties of a civil infrastructure. So they use some kind of different method, like effective independence method, genetic algorithm, different kind of method they use, and some more method can be found here and this reference. So what is EFI? It is used to maximize both spatial independence and sensor signal strength of n targeted locations, means n sensor locations, by maximizing the determinant of associated Fisher matrix information. There are many technical things. I just skip there. It can be found in this reference. This is civil engineering papers. So that EFI method gives EFI values as a location quality. So sensors are placed at locations with high EFI values. Now, what is EFI value? According to those calculations, we can get the EFI values. We rank the EFI values here. So there are some optimal locations with high EFI values, such as in using some structural infrastructure like FEM model, finite element model. When we follow the civil engineering method, so we need to find the location. There are a lot of locations. So we need to find the definite location, such as we consider n locations. We are given n sensors. So we need to find the optimal locations which are with EFI values. So this is our problem. The first problem is, to get n sensors that are placed by finding candidate locations of n using EFI values. So here are the constraints for this deployment, and we want to maximize the lifetime, that is to say monitoring for a long time. So if we follow that civil engineering method, the sensor deployment for a bridge can look like this, using that EFI values and EFI method, just like this. So here, one question is that, can we really monitor the structure with this deployment? There is we need to guarantee that this deployed WSN is able to monitor a civil infrastructure very smoothly. So there are more challenges: data packet losses, weak, strong connectivity, high rate data collection, congestion. So these kind of things we need to care. So those stuff results in energy constraint and also fault failures. So if we look at the fault and failures, we can find that in this deployment, using the civil engineering method, we have some points that we can improve, and that can be points we call repairing points. So we need to find those repairing points that we can improve, and the WSN for SHM can be monitoring for a long time. So here, the points, that is the sensor or communication link failure, are highly possible, such as there are three kinds of points we investigate. Separable points, we can see here, these two sensors. There are many other sensors. They are transporting their data through this way. If one of the sensors fails, that means the network is disconnected. And another sensor is the same way. The second, critical middle points. They are long distance. We can see the communication distance is very high, very long. And another points, we can say isolated points. So three kinds of repairing points we have. If we want to repair these points, that means the network will be monitoring the SHM for a long time. So now, if we can find those repairing points and place the sensor, then we can provide how to continue obtaining adequate information of the structural behavior or changes in the structure, how to guarantee fault tolerance. We need to find some positions, such as those repairing point, we place the backup sensor there. Now, idea is placing a small set of backup sensor by finding remaining unused near optimal locations. Remember that first time we placed the WSN, that one at the optimal locations. But when optimal location is used, so we need to find the near optimal locations to achieve these goals. So now, which are the near optimal locations? These kind of locations are already used. We still see that according to the civil engineering method, there are still some like 0.71 and 0.69. This kind of position still provide high signal strength. So we can utilize these positions for placing some backup sensor. So there is a question may arise the backup sensor can be given extra as the extra sensor, or we can separate. We are given N sensor. We can separate some sensor like backup sensor. First, we place the primary sensor, and then we find some optimal locations for improving the network. Then we place this remaining sensor. Otherwise, we can be given N sensor, and we also can be given another separate set of backup sensor. It depends on the SHM system user. So the second problem is to place a set B of backup sensor into a network with N sensor by optimally finding locations of M minus N remaining or unused locations near the repairing point, such that we can guarantee some level of fault tolerance, also under some constraint here, the communication constraint, connectivity constraint, and data delivery. So this is our primary network. We identify that this and this place are vulnerable. Then we can place some backup sensor here. So this is our same number of sensor. Now you make questions. Why we should not place all the sensor at the same time? Remember that I told you that here we cannot place all the sensor according to the uniform or some other method. If we want to place those sensors, that means we cannot guarantee that the sensor will provide the best civil engineering information. So in that case, we have to follow their method. So we use the backup sensor for this. So we have the 3 points, separable points, critical middle point, and isolated points as the repairing points, and we place the backup sensor there. So here the finding the backup sensor algorithms through backup sensor, we call here the separable points and backup sensor for the find critical middle points and also for the isolated points. Now we have a R number of backup sensor. We use these 3 algorithms. After that, we still have some backup sensor in hand. Should we place those? Now here, this step 2 will check if we still have the backup sensor. If the SHM system user still want to place those sensors, he can use this step. If he doesn't want to place those backup sensors, can save for future users. If this step can be skipped. So this step 3 for connectivity the whole network. So when we find those repairing points, then this part of the algorithm will be used to find the near optimal locations near the repairing point here. So those algorithm is described in our paper. I just skip here. So I described here the performance evaluations. Here we use 100 sensor. We have 100 sensor. We consider the N primary sensor and R backup sensor. So first we place this sensor, then we find some near optimal locations for this backup sensor. We calculate network lifetime and communications, and the network lifetime is calculated the residual energy divided by the number of monitoring round, and using some existing method here. And this is the here the SPM is existing civil engineering method here. It is accepted by Infocom 2010, and another generic WSN applications, and this is our approach. So we compare our approach with the civil engineering approach and also generic WSN approach. We can see here that our approach still can save some communication cost and fault up to 50% failure, sensor failure. So here we record the connectivity 3, and the failure ratio is up to 50%. Means we are given the N number sensor, half of the sensor is given fail. So the rest of the sensor need to monitor the network. So this is the network lifetime. Now I want to show you the real implementations. This is Li Shao Kui building in Hong Kong Poly. We use we place the sensor on this structure. We have the 15 floors this structure we find that using civil engineering approach we find 220 locations, and we have the 16 primary sensor and 6 backup sensor. Here the interest is ambient vibration. So we inject some fault at the 5th and 7th floor. The sensor are given minimum power, and the 2nd floor, after 1 hour, the sensor is removed from the network. We want to see that whether the network can provide the monitoring and what is the communication cost for the network. So here we can see this is the baseline result for original result. The civil engineering approach is here. When there is some sensor failure, we can see the civil engineering approach, the monitoring result is distorted. But under the backup sensor failure, the distorted is minimized greatly. So this is the monitoring result. And under the different fault condition in different day, we verify different day and place sensor. Day 1, we can see the communication cost in day 1 and day 2, day 3. So here, the communication cost is still maximized compared to those civil engineering method and generic WSN application. So here I conclude the paper. We try to incorporate both WSN and SHM requirements that make use of traditional method that is used by civil structure and mechanical engineering domain for resource constrained WSN. I believe that the idea of repairing points, it also can be used for many WSN generic applications. Though there is no EFI values, we can find some other way to use this repairing point for WSN applications. We have some limitations for this work. Still, we need to discuss the theoretical analysis and cost of backup sensor placement for structural health monitoring, network performance analysis and fault tolerance under physical damage detection. Since on a structure or on an airplane, aircraft, we cannot provide the damage in reality. So we need to find a way to provide the physical damage injection and verify our algorithm, how it can provide the monitoring. So we also actually, I just wanted to say, we also have several papers published before on this idea. Here, DSN, and in the last year, also InfoCom the last year, and 2010 also we have several papers on similar idea. So if you have any interest, you can look at these papers. Thank you very much for questions.
Thank you. Any questions? Any questions? Okay, I have a question. So
Okay.
we'll go to slide 25. Yeah. So this is a three-dimensional topology scenario, right?
It is the
Two-dimensional.
data collection is three-dimensional. Yeah.
Oh, two-dimensional.
Yeah.
Okay.
First, the vibration data can be collected in X, Y, Z. So after that, we convert to two-dimensional data. Otherwise, we cannot calculate the monitoring data actually for WSN. If we still want to handle the three-dimensional data for WSN, it costs much energy.
Okay, so is it possible for you to expand your algorithm to the three-dimensional case?
Actually, if we really want to monitor the civil infrastructure, we need to focus on three-dimensional. Otherwise, sometimes the data is distorted. Is still a concern for WSN. Actually, people are proposing the WSN for monitoring civil infrastructure. Actually, there is huge work. We also have several works for that. So, three-dimensional data, handling three-dimensional data is still a task.
Okay. Okay, thank you. Let's thank the speaker.
Thank you. Okay. Thank you very much.
Okay, thank you. So our second speaker is Jürgen Eckert. He's a PhD student from University of Alanya, and the title of his talk is on the feasibility of mass screen relaxation for simple self-deployment.
use it. So, thank you, sorry. Thank you for introducing me. The title of this talk, the paper, is on the feasibility of mass spring relaxation for simple self-deployment. And please let me start with a slide. 1 year ago, from DCOSS 2011, there we introduced our autonomous localization framework. It's basically a framework where a set of swarm robots are distributed in an unknown environment, and they can form a coordinate system in an absolutely distributed manner. And due to this, nodes are allowed to join or leave at any point in time. And last but not least, we are also able to support or to provide localization support for customers as introduced last year for our quad rollers. And last year, we silently assumed that we already have a uniformly deployed swarm in our environment, and today we will shed light into how we can distribute mobile robots in a resource-efficient way, and preferably to do it as uniformly as possible. In the course of this talk, I will show some evaluations done with our broad robot platform as well as with our quad rollers, but our actual target platforms are much smaller though. So here's an example of what they could look like. For instance, the iSwarm project developed from the University of Germany. This here, by the way, is a screw, though they're really tiny. Or maybe a more realistic platform is introduced by Atkins and Halle. And at the time they introduced it, it was probably the smallest Ansys platform, which had no wire, so the battery is behind there. So it's really autonomous platform. And as you can see, we have tremendous restrictions in terms of sensing energy as well as in computation. So what we are here aiming for is a very lightweighted algorithm, and we try to minimize everything. And of course, as we are in the field of wireless sensor and actor networks, we have some additional restrictions, as the movement can only be played based on local decision tables. We only have very coarse-grained measurement information as distances and or angles. And of course, we need to do it, we need to have an absolutely stateless approach, because we do not know what our neighbors or the neighbors of our neighbors are currently doing. And therefore, we would like to use the mass spring relaxation. Mass spring relaxation is basically, the model is as follows. We have mass points, which are basically our nodes. They are connected with linear elastic springs to each other. We have some desired spring length, which is basically the distance they should achieve, and then we can measure the distance. This is the current spring mass, this current spring length, and as you can assume, if you have two mass pointed that's connected together with the spring, and they are too close to each other, as the example is here, because the 0 is actually greater than the 1, 2. As illustrated here, then you have forces which are pulling them apart. These are basically the forces that our keynote speaker already introduced in the keynote today. I don't want you to bore you with the mass and the needed references are all in the paper, so if you're interested, read it. And now we just need to tweak this approach a little bit to get a shape as we want to. We'd like to get such an hexagonal shape because it's best known for its very good trade-off between cost and benefit, so minimizing errors and everything. And the question is now how we can achieve that. For instance, if we get a connection that looks like this, and this node does not connect, for instance, to this node. Okay, first of all, therefore we need some decision tables. So we were able to reduce this decision table to 4 entries. And first of all, we need to define 2 radii, our min and our max. I will come to those in a minute. However, they are dividing our domain around of our node into 3 parts. We're noted the restricted, desired, and attractive zone. And now what can happen is that the following, for rule 1 of our table, by the way, I forgot to introduce that. The first rule that fits the guard, which the guard is standing right here, is elected and those nodes get evaluated for our mass relaxation process. So, for instance, if somebody is in our restricted zone, we evaluate the distance to those, for instance, here node 1 and node 2. We compute the forces, sum them up, basically the same as in the keynote, and then we can compute something like an escape vector, and this is then the direction our node is going, and this node are both doing the same, so this node will go this direction, this node will go into this direction. Basically the same as in the keynote. What can happen in root 2 is that we have a significant amount of nodes in our desired belt. The lambda is defined within the paper. Then we have found position. I come to rule 2 in a minute, so please remember this rule. And if nobody is in the restricted or desired area, and then we start to evaluate the attractive area. For the attractive area, I can say that it can be the area where our detection gets unlinear, so we don't need to have a very good estimation of the distance. We just need to know, okay, there is somewhere a node, and then I try to find it by computing the forces and then start to move towards those nodes. Okay, and last but not least, we need this if we don't hear nothing about any node, so we just have the possibility to randomly drive around, maybe to do a 90-degree turn and move on for a meter or two, depending on the sizes. Okay, those are the 4 rules. Now I need to define both radii for a start. But the minimal radius is some kind of a trade-off between the system costs and the covered area. So this is basically absolutely use case driven. And the maximum radius should be lower than our detection range, as I introduced, because we need this attractive zone. But however, there is an important constraint. So this is basically our base structure here. So 2 triangles connected together. And if we assume the worst case, so all distances are min, then we must avoid that node N4 connects to node N2. If those nodes will connect, we would start to get a rectangle, and this is not what we want, but there the distances, the spring lengths are unequal, and we do not cover as much area as in this example here. Okay, therefore, our avoid is basically just the square root of 3, so times our min. So our max just must be smaller than this equation here. And if this holds, a shape will come out that looks like this. So of course we have simulated this, and now we're coming back to rule 2. If you remember it, we have 2 possibilities to handle rule 2. So if we have enough nodes in the desired belt, we can either continuously move on and by evaluating those nodes and find a better position, or we can pause. So as you can obviously see here, you get a more regular grid out there if you continuously move. For instance, those here are pretty regular. This is what we would like to see. Over there, there are still some nodes missing, so we don't have enough nodes to form perfectly well-shaped hexagon. So this is why this looks a bit ugly, but believe me, as soon as we would put enough nodes in there, we would have a perfectly shaped hexagon structure. And as we stop it, we do not have this perfect shape. However, what you get is a pause and stop criteria. Yeah? And now it's again scenario driven what we would like to have. We've picked 2 examples. For instance, if we have a quad roller which is flying in the air, then energy for hovering is the same as the energy costs as for flying, for moving in the air. So we can still continuously move. Whereas if we have a ground robot, so we can drive to a position, stop in that position, and power down the engine, we will conserve energy. Therefore, we definitely want to have this pause criteria. And as you can see, there is, in both examples, there are equal node sizes, and as you can see, there is a small area effect. And this is why we looked into the area ratio. There are a lot of metrics out there which we need to evaluate. However, we thought, okay, it's about deployment, so it's about area, and we investigated this. So this is basically plotted here is the area ratio. We consider 1 to be the perfect solution, so we have a perfectly shaped hexagon based on a more complex strategy, usually some other issues like global knowledge and a lot of communication issues are included. And we compare this to our continuous movement and to our stop criterion. And for the continuous movement, you can see that over different node sizes, we almost get 90, let's say 97, 98%, so not more than, let's say, 5% of an area loss due to the simplicity of this approach. However, for the stop criteria, this significantly drops, so we only get about, let's say, 20, 80, 85, up to, so at least 80% of the area from the absolute optimal solution. And this is because we use those parameters, so we get a belt around our desired spring length, D0 of plus minus 22%. If we would reduce this to, let's say, plus minus 10%, we would enhance this curve to be around 90%, and if we further enhance it, then we could also reach our continuous movement algorithm. However, the deployment takes longer or may not be feasible due to any accuracy issues, which are again hardware driven and therefore restricted to or dependent on the use case. Okay, as I said earlier, I've already also brought 2 experiments with me. The one experiment here is with ground nodes, and this is some kind of a special experiment because we have fixed nodes, 5 fixed nodes, and we adjusted the distances so that within that area there is no valid position, so that a new node inside of this ring can find a valid position. And usually what would happen if maybe this node or this node would reactivate its motors, drive away, so that this new node can find a good position and stay there. However, maybe due to application, it's impossible because the application wants that the robot is fixed, so it is not allowed to move anymore. This node would continuously drive on and never find a valid position. But now measurement errors can help us, because maybe at this position there is a disturbance, so that we do not measure the distances correctly, or maybe some node is failing, and therefore the vector gets wrongly computed, and this brings us near to our virtual barrier, which actually the mobile node could not reach. And if it's around this barrier, as I said before, the angles also get, or the distance and the distances get very roughly estimated. It does not know whether it is inside or outside of this ring. And therefore, it may happen, as in this example, that we find a valid solution outside of this ring. So this can happen even for this simple algorithm, but we actually do not recommend it. This was just an example how measurement errors can help to solve actually unsolvable issues. Okay, for the last experiment I'd like to show here, we also tried to do it with our quad rotors. So we have basically 4 quad rotors available. And it was a very gusty day, so we couldn't let all 4 quad rotors fly. We had 1 fixed quad rotor. This is because we only use relative informations amongst each other, and as we have wind, then the wind would start to drift the whole network away. But this is here a very short section, about approximately, again, 2 minutes, of a long-term experiment. Let's say long-term is usually quad rotors about 10 to 15 minutes, depending on the battery. And we had a wind gust. The wind was coming from this direction. This node was on a lee side, so the wind didn't affect it that much. It could stay on a position. However, this node and this node could not withstand the force of the wind, and it was driven away. But the connection remained, and as this node was fixed at the known position, so it was basically on the ground, the robot started to come back after the wind was reduced. So this is the little peaks here, and as you can see, the connection remained, and both triangles can be seen. So to conclude my talk right now, we've shown that we've utilized a simple nature-inspired self-deployment algorithm, which is capable of being implemented on ultra-low resource devices, as I introduced earlier. It seems to be very robust, and it can autonomously compensate some real-world issues like the obstacle detections, which I didn't show here, but it's in the paper. If you get obstacles in our deployment, it can be circumvented, and it can be served for ground and aerial use cases as well. However, we do not recommend it for aerial ones because the drones are usually more expensive, and there you can put greater, more powerful processors in. And everything is just based on very lightweighted vector computations, and we do not even need any triangulation functions. We just used some lookup tables from about 4 to 8 entries, and we used a very small decision table of 4 entries. So that's it. Thank you.
Okay. Any questions? Any questions? Okay, so I have a question. So is this algorithm robust to the measurement errors of the distance, something like that?
I didn't get it.
I mean, is this algorithm robust to the measurement errors?
Yeah, definitely is. So usually it's again scenario driven, and as for this example here, we do not average the measurements, but if in general you should take several measurements and do an average of it and then provide it to the algorithm. However, if you do not wish to do though, you can solve such issues. And if we have something like, let's say, a measurement error, the real distance is maybe, let's say, a meter, and they measured about 5 meters. So they will come close together, so this high distance is maybe 3 meters. And this will be compensated in the next step. This is the beauty of the actual approach, the mass spring relaxation, because the next node, which may be here, is also connected with a spring, and it is the same spring constant at this node, at this spring here. And as you pull this node a bit further to node N1, it will get compensated in this spring where the next node is connected to. So if you pull a spring together on the other side, it will pull apart, and therefore it compensates measurement errors very well.
Okay, thank you. So let's thank the speaker again. Okay. Our next speaker is Professor Yan-Ming Zhu from Shanghai Jiaotong University. The title of his talk is Optimal Relay Placement for Indoor Sensor Networks.
Thank you for the introduction. My name is Yan-Ming Zhu from Shanghai Jiaotong University. This is a joint work with my students, Xie Yao and Li Lei, at Shanghai Jiaotong University, and also colleagues, Li Lu and Li Po from Shanghai Jiaotong University and Hong Kong University Science Technology respectively. Okay. So the talk have this outline. Okay, first a brief introduction and also system model, problem statement, and I will present one algorithm to place the relays in the indoor environment. Okay, and finally conclusion. So we consider this problem. Okay, in the scenario in the indoor environment, we are going to deploy sensor network. So we all know sensors will be very common in our daily life, and they will be deployed in indoor environment. Okay, and also recent studies show that a hierarchical tiered architecture will be good for sensor network, because the relay can take the majority of the work to relay the sensor data to the processing center. Okay, so the problem is, if we have many sensors in the indoor environment, and we are going to place relays so that each sensor can send the data to the relay in one hop. Okay. Then how we are going to deploy the relays? The problem, okay, the main problem is that in the indoor environment, the radio propagation model will be very complex. Okay, it is not this anymore. Okay, it is usually irregular. Okay, irregular. So we are solving this problem. We are trying to minimize the number of deployed relays, and also try to maximize the points in the indoor environment where the sensor can be deployed. Okay. So about coverage and the sensor placement, there are a few existing solutions. For example, some algorithms are available for deploying the sensors in a given area so that the whole area can be covered. Okay, at least about one sensor, for example. In this kind of work, the coverage of a sensor is usually much simplified. The coverage of a sensor is a simple disk. Okay, so when this kind of algorithm applied to our problem, they don't work. Okay, they don't work. So there are a few challenges for this problem. So one problem is that in the indoor environment, there are actually many kinds of obstacles. Okay, so one of the main obstacles is actually the wall. Okay, and also there are many different kinds of wall. For each wall, they may cause different annotation to the radio propagation. So we have to take into account the walls when we deploy the relays. And also the relay propagation model, when considering the wall, will be very complex. And we are going to build a model for this. So we have this system model. We consider a given region, okay, a given region, which is two-dimensional. And we use the set W to denote the set of all walls in the environment. Okay? And each wall represented by the two dots, okay, by the two locations of the points, inner points. And also the set of relays we are going to deploy, denoted by K. Okay? And about the propagation model, when we consider the walls in the indoor environment, we use this propagation model. This model actually proposed in the previous paper. We adopt this model. So look at the equation. PSR denotes the power of the signal received at the one point of R. Okay, S represents the sender, R represents the receiver. Okay, so it equals to alpha minus the second item and a plus a tail item. Okay, so the second item really says the power of the signal will annotate along the distance. Okay, so that is a very traditional part. Considering the walls, we use the tail item. So you can see for each wall, we classify into one class of the walls because there are different kinds of walls, some wood wall or some concrete wall. Okay, they are different. So we consider the effect of different wall by class. Okay, by class. So we will investigate each wall between the center and the wall, and consider this affection in the tail item. Okay. So we consider this coverage model because we are going to consider every point in the given area. Okay. So we hope each point in the given area that receive the signal from the receiver, from the relay, can be larger than a given threshold. Okay, so we given the threshold and hope the received signal strength at this point is larger than the threshold. So that is our problem. Okay, we are trying to minimize the number of relays deployed in this given area, and I hope the percentage, okay, the percentage of the point in the whole area is larger than a given value. Okay, we denote this value by omega 0. So that is a formal definition of the problem. Okay. So we prove actually this problem is NP-hard. Okay, we can complete the proof by reducing the minimum set cup problem to our relay placement problem. Okay, so set cup problem is given a set and all the set of sets. So the objective is to find a subset of the sets in order to minimize the sum of all these subsets. Okay, so we can simply reduce the minimum set problem to our problem. Okay, I'll give the detailed proof. And next, I present our algorithm. Okay, so the algorithm have the main steps as shown in the figure. So we have to collect the training data in order to understand the essential parameters for the propagation model. The second step, we consider a set of relay candidates locations and predict or estimate the propagation model, the coverage at these points or of the whole region. And next, we devise one algorithm, we call it RPI algorithm, to select from the candidate locations the minimum set. Okay, the minimum set. So in order to estimate the radio coverage given a set of candidate locations, we have to tell what is the parameter alpha, beta, and also the tail item. So in order to do this, we have to collect a set of training data. Okay. So the training data have to be obtained through experiments. Okay, experiments. So after we have the alpha, beta, and all the tail item, we can do the estimates. Okay, given the candidate location set. And the RPI algorithm, for this algorithm the input of the algorithm has the following. So one, the set of all grid points. So because the given region, there are countless points, so our solution is to divide the whole region into virtual grids. And we consider the grid points. Okay? And the second part of input, that is the set of all candidate locations for relay placement. So for relay placement, we have to consider some points may be infeasible for relay locations. Okay? So this part actually the whole grid point set minus those infeasible areas. Okay? And also the given requirement on coverage ratio. The three parts of input. The main step of the algorithm are the following. Okay, so first, as I introduced, we divide the whole region into grid points, and let L denote the set of all grid points within the whole region. Okay, and also let N denote the set of candidate locations. So A is usually smaller than L. So the main steps of the algorithm are the following. First, we use a set to denote the grid points which already satisfy the requirements. Okay, and the objective actually is to make sure C divided by L and the size of C divided by the size of L larger than the given requirement, the coverage requirement. Okay, so in each iteration, the algorithm greedily select one point from the set of candidate locations into the set of C. Okay, so the criteria for the selection is actually to maximize the current contribution of this candidate location. Okay, so the algorithm select from the set of candidate locations fluidly until the requirements on the ratio of the coverage is satisfied. Okay. So that is the detail of the algorithm. We skip this, and we analyze the performance. Okay, how good can be the algorithm? We prove that this algorithm can guarantee the performance provided by this algorithm is within, okay, a factor of the optimal. Okay, so guaranteed factor compared to the optimum solution. And we do evaluation. We obtain a data set for the reading in a given area, considering the walls, and also we use the following parameters. Okay, so that is a regular floor. The size of the region 47 by 66 meters. Okay, and which in this region includes 65 walls. Okay, in total, and we have 28 tested relays. Okay, so we consider we have so many relays, and there are 100 test points when we collect the training data. Okay, and we compare our algorithm with the two other algorithms. One is random, that is select the location from the set of candidate locations randomly, and another algorithm, that uniform algorithm. Okay, we make sure the selection of the relay locations to be as uniform as possible. Okay, that gives us uniform algorithm. So we compare the three algorithms, a uniform, random, and our algorithm RPI, and we can see given different coverage requirements, we can see the number of relays computed by the algorithm. We can see our algorithm RPI steadily better than the other two. Okay, in different coverage ratio requirements, and also we look at whether this requirement is satisfied. We vary the coverage ratio requirement from 0.6 to 1, and we can see all three algorithms can actually satisfy the requirement. Okay. And also we investigate the impact of grid size, because we divide the whole region into grids. Okay, so we can see when the grid size reduced from 10 meters to 2 meters, the performance of the algorithm fluctuates when the grid size actually are large, and when the grid size becomes smaller, it converges. Okay, it converges. So in our case, the performance of our algorithm converge when after the grid size as small as 4 meters. And also we look at the impact on the real coverage ratio on caused by the grid size. We can see the similar trend. Okay, when the grid size is large, the performance fluctuates. Okay, which may not satisfy the coverage requirement. Okay, when the grid size becomes smaller, it can make sure the requirement is satisfied. Okay, in conclusion, okay, we consider the relay placement for indoor environments, and we propose one algorithm, and we prove this algorithm provide one performance guarantee when compared to the optimal. Okay, thank you.
Any questions? Okay, I have a question. So, could you go back to slide 20? 19. Okay. So, anyway, I just wonder. So, in your experiment, do you assume that the ISS information does not change during the 2 days?
Does not change. Yeah,
Really?
it's still stable. We
Okay.
don't consider the dynamics of the
Yeah, but okay. So, if the ISS information changes, then
we don't want.
okay, okay. Thank you. So okay.
Just go to the result section.
Which page?
Yeah, I noticed the page
one?
Next.
This one?
Here, for example, here. Your result seems to be like in between 10 to 8 grid size per meter. Your result seems to be requires more number of relays. So, what was the factor?
Sorry, can you speak louder?
Actually, I'm talking about if you are considering the grid size per meter between 10 and 8, your result seems to require more number of relays. And what was the factor here? I mean,
The jobs. The jobs.
yeah, I'm talking about the RPI, the result of RPI. Here you can see it requires near about 38, 30.
Yeah, I think the main reason that we don't do a sufficient large number of experiments. Okay, so fluctuations may happen. Okay, because in each experiment the performance may vary significantly.
Okay, so let's thank the speaker again. So the fourth speaker is George Maynard from UCLA. The title is Mitigate Final Effect in Sensor Networks with Multi-Interface Relay Nodes.
Thanks. All right, thank you very much. My name is Dr. Mena from UCLA. This is a work that sort of made my transition from this university when I did my undergrad to UCLA. My advisor is Mario Derla, and my previous advisor when I was in UCLA was Ivana Kadarati. She moved to the University of Athens, University of Economics and Business. Okay, let's get started. Okay, so currently our lab is working on bannings. So most of the projects are in talking congestion, and we have some test beds, we have a Wi-Man station, and that includes the Wi-Fi that spans the campus, the west side. There's also projects on network coding. I'm trying to move onto the initiative of comfy radios, and there's also an area for mobile health networks. So this work is sort of related to the mobile health in the band. So I guess we all know what's sensor network. It's just like for introduction purposes. We have a sensor network, a regular sensor network. We have sync nodes. They're more powerful than sensor nodes. And also, we know that sensor nodes can establish communications to move data inflows across and detect the environment. So the problem that we address, by the way, this project, this paper is like a second part of another paper that I was doing. And the other paper was addressing the overall sensor network connectivity or disconnectivity. This paper addresses the funnel effect, the problem in So basically, we have the funnel effect problem. So we know what that is. Sensors deliver their sense data to the sink, but most of the data that actually gets across is the data from the sensors that are within. This causes of course, that sensors that are remote begins to start. Okay, there's some the resources that they're consuming is bandwidth and power. This is an energy battery power. So and also there's some techniques to avoid this. They use duty cycles, but this when sensors use duty cycles, then the network might get disconnected. So this is probably not a good idea for us here. So my approach is a very simple idea. So if you have a problem with resources, what we do is just add more resources. So here we have a congestion in a city. The city decides to build a bridge, but if that's not enough, they build another bridge. So these are pictures from Mexico City, right? So what I use is a relay node network. And basically, I define it as a relay node as a powerful device that has at least two interfaces, and they can establish autonomous networks because they're connected using orthogonal channels, so channels that don't overlap and don't interfere. So my approach is on top of the sensor network, build an overlay of relay nodes that they can pick up traffic from the areas where the traffic flows from the sensor networks are moving, pick it and move it to the sink. And of course, the sink could be also another relay node as powerful as the relay node. So our problem statement is how to deploy this network, where to put the relay nodes, and how many. Our contribution on this is a placement algorithm, where this is where we put the relay nodes. And we try to approach to the minimum number of relay nodes. I didn't do a rigorous proof on this, but I believe I'm getting close to that. And also, well, I'll just explain about the experience. So my network model is just a regular sensor network. It's a 2D plane with n nodes. The distinction of a node between a relay node is basically the number of interfaces they have. So if a node has one interface, that's a sensor node. It's a unidirectional graph, so there's an edge that goes from one node to the next node. The edges are the links, of course. We have a set of channels available. For example, in the Wi-Fi, we have 3 orthogonal channels, so we could use 3 in this case. And each channel may have available a set CU for node U of the available channels they can connect. And the sensor nodes have a fixed channel, so they don't move around, they don't have the intelligence to do a channel allocation. There's a transmission range set fixed. We define the function d of node u and v as the distance, Euclidean distance. And an edge belongs to the available links if the distance between the 2 nodes is within their transmission range. So nothing new. There's a few assumptions. I mentioned a few. The nodes have channels. They can connect to channels. The sensor nodes use channel C, only one channel. The assignment, channel assignment may be static or arbitrary, or they could use an assignment algorithm. That's not a problem, so we just assume that there's some channel assignment. Relay nodes may establish one overlay or many overlays, depending on the number of interfaces, and they can transmit simultaneously. And for routing, again, this is another topic, but it's an interesting problem because when the sensors want to relay data or move data to a relay node, there has to be a decision. So that's a big problem on its own. So for us, we just did a static. As soon as a sensor node finds a relay node, they just use it. So it's a policy decision. We could address that in future papers. So again, this is a continuation of work that we've been doing. So we already defined, paper where it's a congestion region. So I'm just going to mention where it is. Basically, if a node finds itself congested, and there's some metrics that we use, for example, expected transmission delay, packet loss, jitter. There are several metrics that they can use to determine if they're congested or not. If they get congested, we proposed in the previous paper that there's a spanning tree like algorithm in which they find themselves in a cluster to see if they're congested or not. And this becomes a congested region. So this is the input argument, the input argument for our support in this case. So it's a message exchange protocol. And and we use the convex call because we don't care about the nodes that are inside. We just want to find the frontier where we can start placing the game. So the basic intuition is we have 2 sensors. So we have 2 sensors. This is the transmission range. Okay. So the valid place where we can put a relay node to connect these 2 sensors is where they're intersecting areas. So it's any point in here is valid to connect these 2 sensor nodes. Okay, so given a congested region, This is an example where we already deployed our protocol, but these are sensors. These are our really sensors that we deployed, and this is the same. So if the input is this entire region of sensor nodes, geographical locations. So what we do is first is we calculate the convex hull because we don't care at this point what sensors are inside. Why? Because those are the entry points of foreign remote sensors data field. So we calculate that those list of sensor nodes, and what we do is we sort them such that they are arranged in a ring clockwise order. Okay. And what we do is we cover those. For example, here we put one here that covers those two, and so on, such that all those are connected. And then the resulting positions of relay nodes that we found becomes the input argument for another pass. And basically we're doing rings such that we cover or we allocate paths and we add more resources to find the sink in another direction. Okay, to approach to the minimum number of relay nodes used, we need to define some conditions, and we call it a placement condition. Basically, we want the nodes, we want to place a relay node as close to the sink, such that it's part of the available the reach of the sensor that we're trying to connect. We want to use one relay that can reach the maximum amount of sensors, and also that is the closest to the sink from this region. Okay. So two things right there. Two things: get the maximum number of sensors, and also put it in the at the closest position possible to the sink. So for that we need a term called the node proximity. So basically, doing some easy algebra, we find that the minimum allowed proximity to guarantee that we place a relay node transmission range when it's over 2 closer to the sink is the square root of 3 times the transmission range. So it's basic Pythagorean theorem right there. And we're going to see this in a figure. And also, to control that, we use a parameter that the user decides called extent. So, to what extent the relay node is reaching to the sensors and being placed. So, these are the examples of the node extent. So, if we, the minimum proximity that they could have is this, right? So, they're kind of far apart. So, if these two sensors, if I want to connect these two sensors with this proposed relay location, I have to get closer to the sensors because they're apart so that my reach gets them, but then I'm getting away from the potential location of the sink. But if the sensors are closer, then of course I can place my relay farther and closer to the sink. And that's controlled by this condition. So the distance between these two sensors must be less than the transmission range times the extent. And of course, that has to be less than twice the transmission range because they're unreachable up to that point. So in a theorem, I show that given a point that lies in the placement area, then this point is the closest point that satisfies the placement condition. So let's see that. So this is just an example. It's two sensors, and my sink is way over here, so I'll just put it here to visualize it. So basically, this area is the intersection of these two transmission ranges. It's a valid position. Now, if I put a segment of sensor 1 to the sink, then I have at the intersection, this point intersecting, the transmission range of the sensor. So I cannot place a relay node outside this area, because then this sensor won't get. And the same applies to point B for sensor 2. Okay? So if I put any of these 2 points on these edges, then that wouldn't minimize my distance, right? Because this is the closest point on the straight line. Now, what the theorem is saying is that if the point C, which is the intersection of the extreme points, and the extreme points are the farthest 2 points from the intersection of 2 transmission ranges that are reachable by the 2 sensors. So I have 2 extreme points, and I select obviously the one closer to the sink. What the theorem is saying is that if this point C is inside this area, then that's the minimum point. And we can see that because if we see the angle S2, S1, and C is smaller than the angle of S2, S1, A, so that forces this point A to move away from the sink. Okay? Good. So then we have 2 scenarios where C is outside, and that's our corollary. So if the point C lies outside the placement area, then either A or B would be the best placement location. So this is the case for B. C is outside, so the closer point for the second sensor, the closer point on the segment of the second sensor would be B here, because C would be a little bit farther apart. Okay? And then if this keeps moving along this direction, then it's more evident that C is worse. Okay? And A keeps getting away. We can get it closer to this. Okay, any questions? And the same applies for point A. Okay, so that tells us something about placement condition. Now we want to use a placement condition to use all this information and build our rings, and then connect our rings so we can approach to the center. So basically we start with the congestion region C, that's the location of the sink and our extent value, and what we want is a list of relay values that meet the placement condition. So here's the convex hull, then my stopping condition here is then this is my starting. So I'm going to visit every element in this set such that if it's not covered, I have to cover it. Okay? So if that's not covered, if the sink is covered, if the element E is covered, so I just continue. I don't have nothing to do with it. Otherwise, I find the best placement, the current best place. So I find it, and once I introduce a new element to the set R, I have to see if there are more elements that might be reached by this relay node that I put. So in another inner loop, I visit every element that is already in to see if they're not covered, and this point can reach it. If those points would get eliminated, and then they would be out of where's my point? Here. They would be out of this C button. Okay. And then when this loop terminates, then of course the size of this would have decreased. And then and then this loop terminates, so it's a linear loop even though it's nested. And at the end, I return the point that is closest to the sink between P and P. Okay. And I reverse. So here, this is an example here. The simplest case is when there's an empty node. There's nothing in here. there's only, there's one single node. So in this case, the best position that I can find is just, it lies along the straight line with a distance of r, the transmission range. But an interesting case would be when we find 2. So when we find 2, then I use extent diagram that I explained before to try to connect these two nodes and then be as close as possible. Now, if these nodes were a little bit farther apart such that I violate this condition of r over 2, then I would just perform the simple connection. Okay, because I want to advance my algorithm at least by transmission range over 2. And this is an example where 3 nodes are connected. So the first position valid would be somewhere along here, such that there's a right angle here. But then this node is reachable. So then this node is moved again a little bit, and then the 3 nodes are connected. So there's an imaginary line that goes in here. Then this distance is more than r over 2, so I can connect it. So the node will move from closer to the sink, a little bit farther apart, but still not violating the placement condition. And then I keep continuing. So once this ring is over, I pass this to the recursion again to build this inner ring and so on. Okay, so the main problem, the most complex operation in this algorithm is that I found that it's a complex one, the convex one. Because to perform the convex call depends on the size of the input log h. Okay. The sorting is once I get the size of the convex call is just n log n or h log n. Okay. So simulation results. I use 40 sensors, 1 sink, and 7 feeding sensors that are acting as a remote flow that's going. I'm using Wi-Fi, fixed at 2 megabits per second. And this is pretty much the settings that we found in the Connect 5.0 simulator. We observe the throughput, the delay, and the jitter, which is the inter-packet timing arrival. And we compare it against this naive strategy in which we just put a line and put the relays in. So we observed that using the simplest strategy, we use for our 40 sensors in the sink region, in the funnel effect, we use 24 against 14 in our case, so that's an improvement of about 40%. We run this algorithm several times, so it's just simulated, and we were getting close to all those numbers. Okay, so basically our results are very simple. If there's congestion, we don't see throughput. If there's congestion, if we put the relays, well, there's another network, so of course everything goes back to normal, right? So we just wanted to find that point in which the sensor network gets congested, and we just move on to normalizing the network and just keep moving. Okay? So one network, only using the sensor network, we saw the delivery rate of 81% for all the nodes that were inside, but only 4% delivery rate for the rest, the ones that are outside using distribution. But when we use the 2 networks, we saw almost numbers close to 100% in the delivery rate. So it's expected if you add more resources. Right? So the delay, this graph shows us that with one network, only a sensor network, there's a lot of instability. So things keep going up and down, but again, since there are more resources, the delays go back to normal. So it stabilizes the network. And we see, when we see the jitter, our main gain here is that improves the availability of the data. So the packets here are delivered in an average of 100 to 120 milliseconds. Then, for the normalized network, the delivery transmission, the jitter goes back to normal. And these are conclusions. So all those numbers that I just explained to you, those were our results. We wish to move onto a platform. I will need to buy all these sensors and merge our two projects together and provide some real-life results. Thank you very much.
Speaker. Any questions?
You are assuming like perfect world with circular radio range. Have you thought what happens if the radio range is irregular?
You're assuming what? I'm sorry?
If the radio range is irregular, it's not a perfect circle that you are.
Yeah, well.
Have you thought that your work is extendable or not as well?
No, there's the transmission range is obviously not a perfect circle, right? But in our mind, we're thinking that we could decrease the transmission range such that it looks like a circle. But it's I guess it's our first work on this area, so we don't consider abnormal shapes of the transmission range.
Okay, any other question? Okay, so I have a question. So could you go back to slide 15? No, maybe a little bit. Yeah, previous one. So in theorem 1, let me see. Oh, so that's why. So.
Actually, do you want to see the graph?
Yeah. For this one, so what if the sink is on the same line with source 1, source 2? Yeah.
Okay, then I guess the 3 points would be as close as the C point will move all the way to here. The B point will move away.
Yeah.
And the A point will be here.
Mm-hmm.
So still, this is still the best position because it's the farthest position such that you can reach S1, and then of course it's at the point of S2 or very close to S2, and then the sink is the sink. So it downgrades to the simple line, right, in which we put sensors along the line until we reach a chain, right? It becomes a chain.
Okay, so I think you said that the relay should connect to as many sensors as possible, right? So I think of an extreme example. So for example, one relay connect to one source, and the relay number 2 connect to 10 or even 100 sources. No, then the overall delay would be very large because the second relay should have to wait for 100 or more time slot.
Yeah, so you're saying, for example,
Yeah,
there's so many here.
Yeah, many here, and there's only one source connect to the other relays. Then
That's true.
Yeah.
But also even though there's going to be a lot of contention, right? All those nodes are going to be asking, okay, I want to send my data.
Yes.
Still, there's only so much bandwidth that we can use, right?
Yeah, so you have to wait.
You would have to wait.
Yeah.
But at least the rest of the nodes would not start us, right? So that then becomes another problem, I think.
Yeah, but what if the other relay have those so many sources, source nodes?
Oh, so
So the source node connect to the other relay node.
Well, that's possible. But some of them will fall inside. You see, inside the cluster, the frontier. So some of them would be inside, some of them would be outside. But I'm thinking that if you have so many nodes in a very close region, then that duty cycle is going to kick in, right? And not so many sensors are going to be sending the same data. It's possible.
Yeah, maybe that's some top area with some stagger event happening.
Or maybe
Yeah.
there's data aggregation also, that the sensors inside don't need all to send the same data to the same, right? But still, it's of course it's a problem. I believe.
And you don't consider the interference among those transmitters,
The
right?
interference.
Yeah, in this network. So,
Well, for this node,
so like the source number 2 and the source number 4, maybe they can interfere with each others.
that's true.
Yeah.
Exactly.
Yeah. So do you think I would think of the interference suppression in your
Yeah.
sensor deployment?
That might be possible, but that's the same problem without this solution, right?
Okay. Thank you. So let's thank the speaker again. And now we have the last speaker is Cesar Asan Marco from University of Valencia. And the title of his talk is Network Topology Optimization for Accelerating Consensus Algorithms and Power Constraints.
Thanks, Liam, for the introduction. Hi, everybody. My name is Cesar Asensio from the University of Valencia. And in this presentation, I'm going to talk about how to optimize the network topology in order to improve the convergence of the consensus algorithm. This is the outline of the presentation. First, I will give an introduction of the main concept that we use in this work, like graph theory and consensus algorithms, and a bit of the problem formulation. Then we explain in detail the proposed methods for optimizing the network topology in order to improve the convergence rate of the consensus algorithm. Then I show some numerical results, and finally the conclusions and the future work.
Yeah, but I don't have one.
This is an example of our problem. We have a network of nodes, some initial measurements, and what we want is to obtain in all the nodes the average of this initial data by only using distributed computations as fast as possible, minimizing the energy consumption, and maximizing the network lifetime. In a more formal way, we put all the initial data in a vector that we call x sub 0, and the system evolves using this equation, which means that the nodes that have some initial measurement mix the information using some weights that in matrix form can be formulated like this equation, where the weight matrix is the matrix that defines how the information is mixed and how the system evolves. So what we want is to change something in the process and in the topology in order to improve the convergence rate of the average consensus algorithm, in order to improve the convergence and maximize the network lifetime. As we are considering a random deployment, the nodes only communicate with the other nodes that are in the transmission range, and the problem is that in some cases some nodes communicate with much more nodes than others, and it implies that in general they converge faster, but they also consume much more energy by communicating with much more nodes. So we are considering in this first work a unicast communication model, and in this communication model we take into account three different concepts related with power consumption. The first one is it's related with the power consumption per iteration, which means that it's the summation of the power consumption of all the nodes, where the power consumption for reaching one node I to node j, the power consumption, it's related with the path loss exponent and the distance that separates nodes I and j. We also take into account the lifetime of the network, which is the maximum power consumption per node, and the total power consumption of the process, that is the power consumption per iteration multiplied by the number of iterations that the convergence takes. First, we define some basic concepts. This is the topology matrix, which defines the connections among the nodes. If there is a one here between in the entry sub ij, it's because the nodes I and j are communicating. So there is a 1 here because nodes 1 and 4 are communicating in this case. So and it's a 0 if there is no communication between these nodes. Another important matrix that we define is the Laplacian, which is the difference between the degree matrix, which defines the number of communications of each node in the diagonal, and this is the topology matrix that we defined before. And as we are trying to mix the information, we need to define this matrix, which is the one that defines how the information is mixed. And we define this matrix as the identity minus a constant alpha, and this matrix that is the Laplacian, which is important for the convergence. Here is an example of the value that we can take for the parameter alpha, and here it's an example of this network with of this network with this parameter alpha and with the weight matrix that we defined before. So we take as alpha 1 divided the max, as the node 10 is communication with 8 nodes, the max is 8 because there are 8 communications on the network for this node. Is the maximum degree of the network. So this is the convergence, this is the evolution of the state of the nodes, this is the initial values, and they are trying to reach the average, which is the value over here. And it takes like 23 iterations for an defined error of 10 to -3. So what we want is to change